Hello everyone, welcome back to the channel. This is Dr. P. Today we're going to be continuing with our previous lecture on conservation of mass as it pertains to integral analysis. Today in particular, we're going to work through two example problems, which I know when I solved these problems initially in undergrad, it definitely kind of caused me to get a little bit of a headache, but after having a little bit more understanding, I wrote the solution up and hopefully can walk through with everyone. So I'd encourage everyone to actually do these problems themselves first and then learn from it as we go through the video. But yeah, without further ado, let's jump right into it. So example problem 2. Reducing pipe is shown with an additional outlet as shown below in the figure. So we have inlet 1, outlet 3, and outlet 2. At the inlet, the velocity has a linear velocity profile with the maximum velocity occurring at the upper surface. The flow at the exit planes of surfaces 2 and 3 are uniform. What is the maximum velocity that occurs at the inlet? The flow is steady and incompressible. Great. So, you know, it's like, oh, this doesn't look too bad. And then you see this non-uniform velocity at the inlet, and your brain starts going, wait a minute, I don't know how to deal with this yet. That's okay. We're going to work through it. First step, list out your assumptions. That's something I want to drive home to everyone here. Always list out your assumptions when you are doing like these fluid mechanics problems. And just in general, in engineering, it's good practice. Always list out your assumptions because those assumptions are important when people are checking your work so they can validate, if you assume something correctly. Um, yeah. Anyways, we have two assumptions here right off the bat. It tells us the flow is steady and incompressible. And for this discussion, I think we're going to make the control volume this green region right here, basically the bounding box around this kind of pipe that I'm kind of drawing out in green. And this is going to be a non-deformable control volume. I'm just going to put ND comma CV. That means non-deformable control volume. Don't feel like writing that out. And that's pretty much all the big assumptions. They already told us how our velocity profile should look. We really only have one non-uniform one at their inlet, but the rest of them are good to go. So let's start off with the continuity equation. Let's write it out. Del over del T of our integral over our control volume of rho times dV plus integral over control surfaces times rho velocity dotted with dA equals to 0. Let's start crossing some stuff off. For incompressible flow, density comes out, and we can divide density out on both sides, which basically eliminates it from our relationship. For a non-deformable control volume with steady flow rates, this unsteady term here with the del over del T can go to 0. And then we have our kind of final relationship here, which we saw in the previous video. Integral of our control surface of velocity dotted with our area vector equals to 0. Basically another way of representing volumetric flow rate. So let's go up here now. So let's expand this term into basically individual control surfaces that we have here for surfaces 1, 2, and 3. So this will be, I'm just going to put a 1 at the bottom just because that CS is actually tough to write with this kind of Wacom tablet. So be v1 dot a1 plus v2 dot da2 plus integral v3 dot da3 equals to 0. Perfect. And then from here, we just evaluate all these integrals individually based on what the problem has given us. So obviously the most challenging one with the new concept will be our non-uniform velocity. So let's start with that one just to knock it out of the way. Let's use a different color pen here. Let's use green. This will be CS1. So let's take a step back and really like look at this, not look at the math here. we need to find an equation for velocity in terms of our y direction. And I say y direction here. Let's just assume that x is to the right and y is going vertically up, and these are the positive directions here. Also a very important concept, always label your axes. Very important. So in this case, velocity appears to be varying in the y direction, where at the very bottom of this kind of velocity profile, we're assuming that v is equal to 0, because it appears to go to 0 based on this profile that's drawn. That's a logical assumption. At the top, it already told us that our velocity at y equals to h1, which is the height of this inlet duct, is equal to v1 max. So let's come up with an equation to find the linear velocity profile here. So let's take a look 1 second. So we wrote our coordinates out already. Let's write our kind of velocity profile here. Something like this. And we know from like fundamental math, the slope of a line is just y equals to mx plus b, and this is the line we're trying to solve for here, the velocity profile. You know that y equals mx plus b is the slope of a line. In this case, we're not really concerned about the b component because it's just not going to be relevant, and you'll see why. In this case, our y here is, if we just substitute in this relationship, this will be our velocity in the, just our velocity is going to be a function of y, and that's equal to our slope times y. Basically the same equation here, but we're just substituting in our values. So now we have to find out what m is. So we know that at y equals to 0, v of y is equal to 0, because at y equals 0 here, the velocity is very clearly 0 based on this profile that was written. And at y equals to h1, v of y equals to v max of inlet 1. And basically you can kind of look at this and see, okay, if we made m, it's rise over run, right? Kind of like that's the general gist of slope here. But if you just plug stuff in, let's just start off with v max here. This is times y. If we plugged in a 0 here, that would make vy 0, which is correct. That satisfies this boundary condition. If we put in an h1 for y, that would not satisfy this condition because it's not equal to Vmax there. So what we'd have to do is actually, if we divide Vmax by h1, then if we plug in h1 for y here, those two will cancel. So v of y will equal to Vmax. So this will be our relationship here, v of y. And then we would just basically plug it into our integral relationship here for CS1. And this would be our v of y, which is just I'm just going to write it as v1 comma m over h1 times y, dotted with our area vector dA. Okay, and then that will be equal to, just simplifying it even further, just to make it super clear, vm comma 1 over h1 times y, dotted with our unit normal vector times dA. And I want to make a note here, dA is just equal to our y component. Oops, excuse me, this needs to be a differential here. dy times w, because technically this 2D surface goes into the page by some amount, or out of the page. So dA, we can actually write dA per unit width is equal to dy. And that we're going to plug into down here. Sorry, we're kind of all over the place with these notes, but it's just trying to find space so I don't write on myself in the bottom right corner. And this will be times dy. Okay, and then let's go to a new slide here. We'll just write everything out. So this is CS1, just continuing that again. CS1 will then be equal to let me see here. It should just be equal to the integral. I'm trying to look at my last notes here. 0 to h of, I hate that it does this, where like if I press down too hard, it'll make my pen do that weird options thing here. This would be v1m divided by h1 times y times dy. And this will be a negative sign out front because if we evaluate the unit normal vector, which is pointing outwards like that would be a negative there. And then from there, we can just evaluate this integral very simply. This would just be equal to v1m over h1 times h1 squared over 2. We could cancel out one of those with that, and then we would be equal to negative v1m times h1, all divided by 2, just like that. And I think that's good enough for control surface 1. And as a note, our area here, once again, is per unit width into the page. So all of our terms here. So anytime you see a dA, assume you're kind of just like dividing it out by the width of the page and only focusing on the other component of that control surface. So next, let's go over to control surface 2. So for control surface 2, we have the integral of 2 of v2 dot dA2, which is just equal to the integral of v dot n dA. Now, in this case, because your unit normal vector is pointed in the same direction as velocity here, the angle between them is, again, 0, so we'd have a positive 1 for this term here because it's outflow. Our dA in this case, because we don't have anything changing with respect to area, everything's fixed, the height is fixed, the velocity is uniform, dA could just be equal to h. Or dA over W can be equal to h2, which is equal to v2 times h2. And then if you do the exact same thing that we just did, you'll end up getting that CS3 is just equal to v3 times h3. Literally the same process we just did for this, but in this case, the unit normal vector is just coming at a slight angle, but so is the velocity. So the angle between them is still 0 degrees, and you have a positive value here. So if you bring all the terms up together, kind of going a little bit out of whack here, you get something like negative v1m times h1 over 2 plus v2h2 plus v3h3 equals to 0. And then from there, all you're doing is solving for v1m and plugging in your numerical values to find out what v1m actually is. So let's take a pause here and go to the next slide so I can finish writing this out. So all I'm going to do when I rewrite this is I'm just moving this negative term over to the right side to make everything positive and reevaluating it. This will be v1 comma m times h1 over 2 equals v2a2 plus v3a3. And then you just solve for v1m. This would be 2 over h1 times v2a2 plus v3a3. And after you plug in all your values to this relationship here, you get that v1 max is equal to, do a calculation really quick, 3.8 meters per second. Cool. So that's pretty much it. Again, not too crazy. The only kind of weird part for most people is dealing with this term here and trying to evaluate kind of expression. And I don't, I totally understand that. If you need clarification on this, please, again, leave a comment below. This can be a little confusing, but to quickly summarize for this problem, you know, all your velocities here have to be accounted for in terms of integration. So if you have a uniform velocity over a fixed area, you don't have to actually integrate because nothing is changing over that surface area. But in the case of inlet 1, we had a varying velocity over our area, meaning we did have to use our bounds of integration and integrate. And we had to create an equation for our velocity as it was varying over that surface area, which is what we did right here. So sometimes you'll be required to develop your own equations. Other times they'll just give you the equation, which you'll actually see in the next practice problem we go to. Okay, so let's move on to our final example here. This is example problem 3, and I think this one's actually pretty easy. And I say that obviously knowing the answer, but it can be tricky. Just really lock in on what the question is asking, and you should be okay. But definitely try solving this yourself before you see the solution. So let's get into it. The boundary layer of a viscous liquid flows steadily down the inclined ramp. If the general form of the velocity profile is known, find the mass flow rate per unit width in terms of density, dynamic viscosity, gravity, angle, which is theta, and height. So you might be looking at this and be like, well, wait a minute, this is very confusing. I don't see a control volume. I don't see well-defined walls. What is going on here? Well, don't have to worry. You got to look at what the question's asking for. The question's asking you just to find the mass flow rate. It's not asking you to evaluate a certain velocity. It's not asking you to find a certain area of where this flow is going. It's literally just asking, what is the mass flow rate based on this velocity profile we have here? You have a bounded region of space. You know that your height of your profile is h. You have a velocity profile. That's all you need. Nothing else. So, what's mass flow rate? Without even going into conservation of mass, what's mass flow rate? It's just equal to your integral over whatever control surface you're looking at times the density times the dot product of velocity times dA. That's all it is. So in this case, we have everything we need. We have velocity, we have u of y, and our area, in this case, again, it's a 2D problem. So our area is going to be per unit width into the page. Okay, so area is just per unit width. That's all I'm saying here. Let me erase this little one here because that could be a little confusing. So once again, we have a varying velocity that varies in the y direction, assuming this is our tilted coordinate system here that is positive. So we have to take our velocity and plug it in directly to our velocity vector here. Additionally, we have our kind of area here, dA, and dA will be equal to the normal vector times the scalar area differential, and that's going to be equal to n, in this case, dA is per unit width, so we only really have to multiply it by the height at which this kind of velocity profile is taking up, and that would just be equal to h. So that would be n times h, I think. Or you could just call it dy if you wanted to. Now I think of it. To be more mathematical, we'll call it dy. Eventually, it'll end up working out to h, but we're going to use it as dy because, again, velocity is varying in the y direction, so we have to use a y differential here. So let's plug everything in and just start solving it out, and we'll talk through it. So m dot is equal to our control surface integral. I'm just going to keep it as an integral now. I'm not going to write cs of rho times our velocity, and that's going to be equal to rho times g times sine theta divided by dynamic viscosity times hy minus y squared over 2 dotted with our normal vector times dy based on what we saw up here. So let's just assume that our control surface, because technically we have to evaluate this at a control surface. Let's assume that our control surface is here, this kind of line here, and we have outflow from our control surface to the right. So it's flowing out of this little control surface here. We don't have to worry about a volume. Technically, if you wanted to make a control volume like here, it wouldn't matter because we're only evaluating the mass flow rate here. And I like to work with a positive value, so we're going to work with the outflow value there. But realistically, it would be the same. So with that, let's just kind of simplify this a little bit. So this would be our integral of rho squared times g times sine theta over mu. Kind of sad that row didn't write as I really wanted it to there, or my fraction kind of looked a little bit messed up. Let's do something like that. There we go. That's better. Times hy minus y squared over 2 times dy. Almost wrote a dA there. And then from there, I mean, this is pretty straightforward. I don't want to really work through all this. I mean, I guess I could just to make it easy because there's always going to be that one person's like, where did that come from though? So all I'm going to do here is just, it's basic math. You just pull out this fraction because it's constant outside the integral, and you evaluate this term here with respect to dy. So this would be equal to rho squared g sine theta over mu integral, and we're going to evaluate a definite integral because we're integrating from technically y equals 0 to h, 0 to h, and that would just be hy minus y squared over 2 times dy. And at that point, basically after you evaluate this integral, this becomes h times y squared over 2 minus y cubed over 6. You plug your definite bounds in after evaluating that, and you would basically get that your mass flow rate is equal to h cubed over 3, which comes out from this integration, and then times rho squared g sine theta, all divided by mu. And that's it. So this is actually, I mean, this is a really straightforward question, right? It looks very daunting with how it's all set up. And I mean, I'm pretty sure I got this question wrong when I first did it because it was just very confusing to me still. But when you break it down, I mean, all it is just plug and chug. You know, this is what trips people up a lot. The velocity being kind of tilted at an angle. They're like, oh, do I have to consider it at an angle? No, not really, because, yes, you're at an angle, but your velocity profile that you're given already accounts for that. And your coordinate system that is given to you is already tilted. So you don't have to worry about, evaluating this velocity vector at, an x and a y component or something like that. Um, which trips people up. And then the other thing that trips people up is the area being a per unit width value. It's hard for them to imagine that area is just kind of like the height, and kind of not picturing that this has a width into the page or out of the page. But once you get those two ideas ironed out and learn how to plug it in, it's really not too bad. So yeah, that's pretty much it. That was example problem 3. In the next video, I'm probably going to do 2 more questions, but those questions are going to be pertaining to situations where you would use like a deformable control volume, where your flow is changing with respect to time, which are a little bit more challenging, but there's 2 common questions that are, uh, I guess, normal in most of the classes that you'll take for fluid mechanics, so we'll try to address 2 of those, and hopefully you'll get the gist. Anyways, thanks for watching. If you have any other comments or something looks wrong with my math or something, just leave a comment. I'll try to get back to you. See ya!